Good morning, everyone. Welcome back to another installation of AI BDS1. So today, what we're gonna do is we're gonna continue. We're gonna continue to talk about the core element of machine learning, which is the actual learning procedure. And so what we did last time is we started to explain one crucial component of the learning process, which was the cost function. And I'm going to start by summarizing what we discussed last time. And then we will today discuss the second important concept, which is the actual learning process, which is the learning algorithm that helps us to actually teach the model. So actually find the parameters, which is the goal, right? And this is called gradient descent, and we will explain why we need it, why the cost function plays an important role. But before we do that, let's summarize what we talked about. So generally, we have this analogy that we train a child to detect what a sports car is, yes or no, whether a car is a sports car, yes or no. And generally, what we have is like we have this form, this empty hull of a child, right? That is not trained at all. So at the beginning, so what we do is we choose a child that can potentially like be good at this, right? And this is the hypothesis. So this is kind of the form, right? So this is the form of the hypothesis or the hypothesis, right? Um, so the form is just how the parameters are going together. How they are like, for example, there is a plus here, they are not multiplied. So this is the form of the hypothesis, right? And the form of the hypothesis is constant. Like this is something I have to decide in the beginning. This is very important, right? And the form of the hypothesis here is called linear regression, right? So linear regression. So when we say we're going to do we train a linear regression model, we mean our form of the hypothesis is a linear regression. If we say we're going to train an artificial neural network, then we have another form. However, what we are doing essentially, these steps with the hypothesis, the parameters, the cost function, and of course our goal will always be the same, no matter how complicated the form of the hypothesis is, right? So we could have like these large transformer models, but in general, it will still always be the same idea that we have. However, it will take maybe some more steps to achieve this actual goal. However, it will always be like this idea in supervised machine learning. So this is like the gist of supervised machine learning. Supervised being we have our training data set. So we have X data, which is our features, the X data, and we have the truth, right? We have called it ground truth in having the Y, the solution. So we, for example, for the child, we say, hey, these are the features of the sports car, but we also tell the child, hey, this is a sports car, this is not a sports car. So we take it through the parking lot and we will tell the child everything. And then the child trains to detect sports cars and then can go to a potential new parking lot and tell us what is a sports car, yes or no. So this is the idea. And then we talked about how could we achieve this and what kind of parts are actually the things that get trained, right? So as I said, the form of the hypothesis, so how they work together. So this one here, like the plus and how many X we have. So this is the form of the hypothesis, right? Of course, the form of the hypothesis is very general. So here in linear regression, we just say, okay, this is a linear model. So we say, okay, all our variables together with the parameters are chained by addition. So this is a linear model, right? We don't multiply them or anything, or we don't like the parameters are not in the power or something, right? So this is a linear model. So all the components of the model are like in a linear relationship with each other, right? So we have a linear relationship between our target variable and the feature variable, right? So it's a linear relationship. Okay. Um, so this is like the idea of a linear regression, right? So, and so this is the form of the hypothesis. However, now we want to train this model, right? So, and there was some question last time, and I think best explained is that the training of a model is a process, right? So it's not like here it is, but it's a process, right? And I think we started like this timeline. So we have the form of our hypothesis, and our hypothesis, the only thing changes in our hypothesis are the parameters, right? So the parameters are the things that change. So of course they are in our hypothesis. So you can see theta 0 and theta 1 are of course in our hypothesis. And they are the ones that change. Like the parameters, they change. And the parameters are the things that get trained by the learning algorithm. So whenever we talk about parameters, these are the things that actively get trained. And this will be true for neural network, for everything, right? The parameters are the ones that get trained. So basically, this is the thing where we just have to I'm going to say just to make it easy, but where we just have to click and say, hey, train this, right? Give the data, train this, and we don't have to take care of these at all, right? These are the things that come from machine learning. The result of machine learning are the parameters of the model. This is very important. So how does our actual y variable go together with our x variable, and we're gonna train the model, and these parameters determine how they go together. The form, the actual form, like the relation form, this is dictated by the form of the hypothesis, which we have to set before. So there is still a job that we have to do, right? So we need to select, form. We also kind of need to select, this is why I put the x in here. We also kind of need to select uh, what kind of variables to put in here. For example, I could also like put in other variables. As you know, our example were housing prices in Portland, Oregon, and we had like the square feet as an x variable and the price as a y variable. So our hypothesis tries to predict the housing price by having the square feet of the house as an input variable. However, if I would have asked you like last time, or I could ask you this time, hey, do you think this is a good model? And you would potentially have said, well, this like we need more variables. Um, and just to think about it, when you want to determine the selling price of a house, right? So let's go maybe to our example. Like we had this example, we had the size in square feet. So this was our x variable, and our y variable, as it also says in parentheses, was the price. And we want, of course, to predict the y variable, right? So this is the basic idea. And so just centralize this a little bit. This was the central idea, obviously, right? So, and by being able to do that, we could potentially help the real estate agents come up with a price for any new house that we want to predict. So this was our idea on building an AI-based system for that. So now, if I were to ask you right now, do you think this is a good model? Or what would you improve? What would you improve? Like, we're gonna build this model here with the hypothesis, and we're gonna put in size in square feet as an input variable. Like, what would you improve if it was your job to build that model? Like, you are hired, you're an IT or data scientist, and you are hired by a real estate agency to say, hey, we need a model for the market price, the selling price of a house, right? What would you say? How would you improve that? Like, you can write in the chat. So this is just a little bit of analytical thinking, so that we don't lose it while we while we discuss how the models are trained. So how would you maybe improve that model? Or maybe you can also tell me why this is not a good model, right? Or why the model will not be a good model, particularly. So if you think about what goes into the selling price of a house, like think about your flat or think about houses in general, how would you determine their price and how could we improve that model, right? So feel free to put it in the chat while I scroll down again. Sorry, here. Okay. So specifically, I already kind of told you, but I think we have add variables like amenities or the neighborhood. Yeah, exactly. So basically what I did here, like you would not like have a model with one variable probably, right? So having one variable is not gonna cut it. Like a big one definitely is the neighborhood. So where is it? Like the same house in standing in San Francisco will be worth way more than standing in somewhere else like Wisconsin maybe or something, right? So that depends where the house is located. Also other things like number of bedrooms, for example, than the size of the lot the house is built on, and so on. So there are countless other examples of adding variables here. Okay, so this is true. Thank you. And so basically, however, this is something that we would have to do, right? So we would have to say, okay, this is my data table that we got from data preparation, right? We followed the CRISP-DM process. And at the beginning, we were like, hey, we want to, our data mining goal is to build such a model. And now we would think about what kind of variables to include and to not include. And this also, right? This also means that we could potentially include other things like, and this is like somewhat a misconception. We could, for example, have like x2 squared. Like you say, but Kai, this isn't a linear model now. But it is because the components are still linear, right? So the parameters are still linear. Like the thing I train are still in a linear relation, right? The only if I square this is just a number, right? So this is just a number I square because I have x, I have the x values. Like if I do something like this, then it would be nonlinear, right? So this would be nonlinear. Um, but if I do this, that is just the input, right? So I just do feature engineering, right? And I could also do something like an interaction effect, right? And I could also do something like this. I'm just making, but it's my job because this still belongs to the form of the hypothesis to put this in, right? So I know that in front of each of these combinations, I will have a parameter. They are, of course, different because the influence of that is measured. The influence of every input is measured. So these are all the inputs here, right? And so, and there are different parameters, of course, because the input of this is obviously different. So we have different parameters and they get trained. However, I need to decide what kind of components my model should have, right? So it's very important. And I want to open up this discussion right now because we will have this discussion in the next semester when we talk about deep learning, because then it kind of shifts. So as we know, this form right here and linear regression is a sort of shallow machine learning. And shallow basically means we have to do this. Like we have to directly connect somehow. We have to directly put out the form, right? So do not have to think about the parameters, right? So this is trained by the model. So this is nice. However, we have to decide what kind of input variables go in there from our data set, right? In deep learning, we kind of, and this is a very loose definition of deep learning, in deep learning, we kind of just throw the data in there. And these kind of features here, right? These, apart from the features themselves, like the X1, X2, of course, this we have to put in. This is our basic data table. But this is feature engineering. Like we could just, this is just creating a new column, right? Where we have X2 in the one column and then we square it in another column. So it's just a transformation. It's a data transformation. Something we could potentially do in the data pre-processing also in feature engineering, right? So what I'm saying is when we go from shallow to deep learning, it will kind of shift. So, but having said that, what's important is that the form of the hypothesis is what we choose at the beginning, and we choose the form of the hypothesis, and we kind of choose what goes into, like the input variable that go into the form of the hypothesis. So these are two separate things. Can also talk about the architecture, right? And this will be specifically true when we talk about like deep learning model. There it is actually called architecture, but it's also architecture here because we have some things that we have to choose, right? And there are things that the model will give us due to training, right? And these are the parameters that we'll learn. So, and why am I telling you this is because it's important for you always to know what you have to choose also for practical reasons. Simply if you implement it, what you have to choose and what the program does for you. Like everything we discuss, what is your job and what is the job of the learning algorithm, right? That you have implemented. So it's very important to pick this apart. Like no learning algorithm will say, hey, include x2 squared. This is something you have to decide. However, the parameter, so the influence of x2 squared will be learned by the model once you include it, right? So, and then we ask ourselves, okay, how could we learn these parameters? And then I said, hey, we watch it kind of a timeline, right? So since this is the only thing we change, we start with, I think I called it the stupid model, like just to know, okay, this is or the starting model. So this is we start training here, and this is like whatever. This is like maybe after 100 training cycles, we say, okay, this is the final model. And so here we will have our first set of parameters, right? Let's call them 1, 1, first set of parameters. And then we're gonna apply our training procedure, which we will learn today, right? And then we're gonna have steps like here. We're gonna change it like this is the second step, right? 2, this is the second step. So they will take on different values, right? And so on and so on and so on. Like here we'll have, and then at the end we will have like after 100. We will have like after 100 cycles, we will have the parameter combination that might be really good. And the only thing we talked about last time is we kind of saw this like a progress when you go to the gym. New Year's, you decide to go to the gym to become strong, and you start out at a total zero, right? You start like no muscles and so on. And then you improve from week to week, you improve, right? And you get better until you have achieved your goal, which, and like your muscle size or your ability to run is measured by these parameters. These are the parameters, your inner workings, like your physiology, your muscles that drive how good you can perform, right? So this is like your body basically. And these are like your body parameters, and they improve, right? And so what we do is we need to measure how they improve. And this is what we did by implementing what's called a cost function, right, in machine learning. So for each step, right, for the zero step, we measure the cost of this, right? So we measure the cost of this. And so what our goal is, with each step, the cost should go down, right? So we should get better. So basically, we measure the cost of this, we measure the cost of this, and so on, and we measure the cost of this. And this cost is the minimum cost, like of all of them, right? And so this is basically our goal. Is like this is like a fitness test your trainer does with you, and then we could kind of relate to that and say, oh well, you have improved, right? And so this was the concept that we talked about, right? So the cost function, and like this idea that we change parameters over the course of the training. And this is the same in machine learning, right? In the machine learning, it's exactly the same. So we train, we also have, we will talk about a little bit later on how many iterations, like how many of these things do we need, and so on. And how can we configure it? Is it always good to have a lot of them? And so on. Specifically in deep learning, we will talk a lot about this training procedure. However, so we talked about this cost function. And so this is the next, as you see, this is the next thing, is the cost function. And so the cost function is a measure of, how fit we are, and we hope to improve this. And so the cost function sums up basically what the cost function is, and this was like a summary from last time, is it always compares the ground truth, like the true Y value, the ground truth. So this as it what it should be, right? What it should be. So imagine in a gym, someone your trainer looks like and says, okay, you should be able to run 5 miles now in that time. Right? So this would be the Y variable. Your trainer says, hey, you should be able to run that. And this is the time you really ran, right? So this is your inner workings. This is your inner parameters, right? Because to see the hypothesis, which is that, contains our parameters, our muscles, which basically determine how good we are, right? How well we perform. And so, and the trainer compares the actual ground truth, so what you should be able to do with what you are able to do. And the smaller that difference is, the better, right? If this is zero, it's perfect. Like if you can actually do it, then yeah, you've trained well, you've achieved this already, right? However, if this is large, that it means you need more work. We need to change the parameters, because this is the ground truth. This, of course, we cannot change, right? So this is how it should be, and we need to get closer to how it should be, by changing the parameters, right? So what we actually do is we're gonna change the parameters, and our goal is to minimize the cost function, right? So obviously we want to minimize the cost function. So we want to, in our case of linear regression, it's pretty easy. So we want to minimize the costs because, yeah, well, minimize cost means best model. This is our determination. So, and we have two parameters, means we want to minimize want to minimize this cost function regarding theta 0 and theta 1. So we change theta 0 and theta 1, and we hope for a nice cost function. Okay, so once again, let's have a look at what this actually means. So as you know, I love this visualization where we have our hypothesis on the left-hand side and the cost function on the right-hand side. And why I do this is because I want to stress the similarities and differences, right? So this, of course, is a function of x for fixed values of a parameter. Like whenever we have parameters, we get like a model. Like this is one version of the model. And the cost function shows us for a lot of these models the cost, right? It shows us the cost. So each point here, each point on the cost function is one of these models, is one h of x, right? So I have a lot of these and I can put them in. And to show you this, I'm actually gonna use colors now. So let's have a look, right? So we're gonna start with this, right? So we're gonna start. I'm gonna just draw it. Let me just draw it a little bit thicker here. Okay. Okay. Yeah, this is better. Okay, so this one right here, right? So this one right here. So we have this model, and this model is determined by some sort of parameters. Now, for now, so we can do it in two-dimensional space, we're gonna ignore theta 0, right? We're just gonna say, okay, we're gonna change theta 1. So, and for this red line here, we have theta 1 equals 0.06. So it's somewhat here, right? So this is theta 1, it's 0.06, so it's somewhat here, right? So this red X is that model, right? So this is that model. So we have a fixed theta 1, and this is that model. Now, and we see the model is not particularly the best model we could have, right? Let's say we have another model. Let me do a pink model, okay? Let's say we have this other model. So we have kind of this model right here. It's kind of this model, okay? So we have this model here, okay? And so this might be even worse, right? So it's even closer to 0, right? Okay, let's have another one, better one. Let's say this right here, okay? So this might be closer to here, okay? So what you see is that for each particular model, right, on the left-hand side, we have 1 point on the cost function. Like we measure how good this model is by the cost function. So how good is this parameter combination? And basically, if we look at this, what we have is probably the green one is probably close to here. Then the pink one is probably very at the beginning, and the red one was also very at the beginning. Oh, sorry. So, right? So that you can see, this is like the way it goes. Now we improve this. So basically, we improve the models step by step. So this is how we do it, right? We improve the model step by step until we somehow achieve a good model that goes towards like this minimum of the cost function. And this is the minimum. The cost function, just do it smaller. So the cost function minimum is kind of here, right? So let's have a look, just so you know, how it would look like if we actually consider both parameters. So we're going to use what's called a contour plot, right? So this is a three-dimensional thing, so that you know how it would look like in the three-dimensional case when we do not ignore theta 0, right? So as you can see, it's basically the same thing like this, but three-dimensional, right? So the cost function, we know that the cost function is a squared function. So it looks like this, like our normal squared function, like the things you are used to when you had like basic math, right? It's just a three-dimensional version of that, as you see here. And also here, we try to go down somewhere here, right? We try to find the minimum here. And we try to find the minimum of theta 1 and theta 0. So we need the combination of both to find the minimum. Okay. So, and what you can see here is like these are contour plots that can actually, where you actually can see the three-dimensional in a two-dimensional space. So, and what we try to do is we try to move here, right? So we try to move here. And this is the same thing I just did here in a two-dimensional space. This is the same thing, but in a three-dimensional space, right? It's exactly the same thing. So we have different points right here, and we try to move towards this point, right? So this is the idea. So we start with the bad model, for example, here. That is somewhere here, and then we're going to change it, and we get another model, and so on. We get another model, and we try to find a model that we will somehow arrive at this point. And this is like the idea on how we're going to do it, right? And now the question is, how do we do it, right? How do we achieve this? How do we go from like the pink one to the blue, to the green one? Why has the green one disappeared? Sorry about that. Why is the green one? How we go to the green one? So this is the question. And this question is relatively easy answered because what we're gonna do is we're gonna just, and you've guessed it, right? You've probably guessed it. So the outline is what we're gonna do basically is we have the cost function that we know. So the cost function tells us how good we are. So what we're gonna do is we're gonna start with some theta 0 and theta 1. Remember the pink one where we start with really bad, where I say, okay, we start somewhere. This is like after New Year's, we come in and we start somewhere. Like we're in really bad shape or we're in some shape. And this is how we start, right? We're going to, for example, we could start with 0. Like they could be 0. You asked me last time, hey, what would be good start values? Well, 0 could be a good start value. The start value is just a random start value with no idea, right? We have no idea, okay? So then we change them. We keep changing them to reduce it, right? So want to reduce this cost function. So we're going to change the values to reduce them until we hopefully end up at the minimum. This is the idea. So the only thing we really need to know, what do we need to know? I'm going to ask you. Now, if you read this outline, right? If you read this outline right here, right? What kind of thing, where would you ask a specific question? Where would you say, okay, but how do we do that, right? So how do we do that? What's the burning question here? And it's very important that you think of this by your own and say, hey, this is the burning question I would have immediately when I see this, right? So what would be your burning question here? I mean, obviously, this is not a clear. This is just an idea, but this is not a clear instruction, right? We need a how. So, what would be your burning question here? How to change women? Exactly, Max. This is exactly. So it says, hey, we keep changing, right? It says we keep changing how to change and reduce theta. Exactly. So, one very important thing. One very important thing, right? I have to say, like that there are no misconceptions, right? We don't reduce theta. We reduce the cost function, right? So the cost function needs to go down. The theta values could go up or down. It doesn't matter. It depends on the cost function, right? It depends on this. The theta doesn't go up. So theta can go up or down. It depends, right? But what always goes down is the cost function. Very important. You have to distinguish between the parameters. The parameters are just the values here, right? So the one parameter is this. This is theta 0, right? This is theta 0. This can go up or down. It doesn't really. So, and then the other thing is the slope, right? Theta 1 is the slope. And and we don't have to like minimize these, but we minimize the cost function. Very important. So um, it's not like that we have to drive theta down. We have to drive the cost function down, right? And it depends, as you see, the cost function is a function of the ground truth, right? So it depends on the ground truth what we have to do with theta. If they have to like be larger or smaller. So it could also be that for some scenarios we have to like drive theta down, and for some we have to drive them up. So it's very important that we don't necessarily reduce theta, we change it, right? So keep it a change just to make sure you understand, right? We drive J down. The cost function goes down. This is the only thing that matters, right? So, but yeah, valid question. So how to change theta, how to change the parameter. So the only thing that we say here is we're gonna keep changing, but how? So, and basically what you are asking is which direction, like we even saw in the comment, to say, hey, do we need to reduce it? Do we need to make them larger, the theta values? And this is the burning question. Like, how do we change it? Like, what direction do we change it? And the magnitude, right? So magnitude plus direction. Like, is it plus or is it minus? Like, do we reduce them or do we enlarge them, right? So, and so basically the idea is the following, as you can see here with another example of the cost function. But let's do it in a simple way. So what we do basically, is it's very simple. We go down the cost function, right? Because the cost function, the direction, like we're gonna keep changing them in the direction of the cost function, right? Depending on where I am at the cost function. So we're gonna start, we have this starting point. This is my parameter where I start. This is my form when I go into the gym, right? And depending on that, where I am, we're gonna drive down the cost function. And this is basically it, right? So before we're gonna read about how gradient descent works and about this formula, let's make it intuitive. Okay, let's make it really intuitive. Okay, so we have this cost function right here. Okay, so cost function j of theta. Okay, let's do a j of theta 1. Again, we ignore theta 0, so we can do it in a two-dimensional space. For the three-dimensional space, it will look something like this. Okay, so very easy. Now, so what we're gonna do is, so we know that we're starting somewhere, right? So we're gonna start somewhere. So for example, we're gonna start here at this point, right? So this is the point where we're gonna start. So this is theta. This is our first theta 1. We can also say we're gonna start at 0. So if you say, hey, but you told us so we can start at 0 or near 0, so we start here, okay? So I don't care. We can also start at 0 if you like. Like we could also start here. When we said, okay, they are both 0, so we're going to start at, for example, 0. We can also do that. I don't care, right? So we can also start here if you like. But we will have both scenarios, right? So let's start here, and then we're going to have the same starting here. It doesn't really matter. So, and now we want to improve. Like your question, your burning question was, how do we change it? We start somewhere, and how do we get better? Well, we change them, and we go down the cost function. And how do we know what down is, right? How do we know the direction? How do we know what down is? Well, it's pretty easy. So if we have this point, we're going to draw a tangent right here. So this is basic math. We're going to draw a tangent right here. And we have the direction of the tangent, the slope of the tangent will give us the direction. It's pretty easy. And like the concept I just introduced, I didn't introduce it really, is called the derivative, right? It's the derivative of the function that does exactly that. It shows us the slope of the tangent, right? It's the derivative of the function. Like, you know, this whole thing, how infinitesimal, like derivatives are motivated. This is it, right? So basically what we do is we're gonna drive down here. And the same thing, so we're gonna know this thing right here, right? We know this thing right here. And we know if we look at this, we can see the direction. So we can see the direction of this whole thing, right? So we see this right here. And what's the slope of this thing? Like, is this a positive or a negative slope? Is this a positive or a negative slope? The slope of this, positive or negative? Yeah, it's a positive slope. Exactly. So now you would say, hey, but if it's a positive slope, we're gonna basically, but I need to move it to the left. So I need to reduce the parameter, right? So if it's a positive slope, I need to reduce the parameter, right? And here, I promised you we would also had the same thing here. Now here, This one, I think I don't have to ask you. This is, of course, a negative slope here. Sorry, I cannot, obviously, I'm not able to draw lines, but this is a negative slope, right? So this is a negative slope and this is a positive slope. So what we're going to do is we're going to use the slope to change the parameters. But obviously, we want to arrive here. So we want to change, like, for example, let's say we're going to move this one to that one, right? So we're going to have this to that. So this is theta 1, 1. We're going to start here. And then I'm going to move it more towards the minimum, right? I'm going to move it more towards the minimum. And let's say in my second timeline, right? So with my second timeline, I mean this one, right? I'm going to move it in the training procedure. So, and I'm going to move it towards the middle, right? And the same is true for this thing right here. So here, if I start here, right? So this is theta 1, then I could potentially move here, right? And I would get more closer to the middle. And now, and this is how it works. And so what I just told you is create a descent algorithm. So the idea that we have is we start with some theta 0 and theta 1, right? We're going to start with some theta 0 and theta 1. And then we're going to update it. It's called updating. So we're going to update the parameter. So we take the old parameter right here. So with old, I mean the starting parameter. So we're going to take this one right here. And then we're going to do minus. Aha, minus. So now it works. If we have a positive slope, it goes towards the middle, right? If we have a negative slope, it also goes towards the middle. So now it works because we have this minus right here. We just use minus. So we update this. So this is our parameter. Then we have minus. Then we have a thing called alpha, which is called the learning rate. We will talk about this in a second. And then we have the derivative right here. And the derivative gives us, influences the direction, right? The direction in which we go. So this determines if we go here or if we go here, right? And this is the important thing. And this is what the derivative does. So if we start on the left-hand side, in this case of the cost function, we start on the left-hand side, right? The slope will be positive, meaning minus a positive slope. So I can tell you that the learning rate is always positive and between 0 and 1. So this right here, this thing right here, is always like this thing right here. This thing right here, we say here, so this derivative has either positive or negative slope, right? Either plus or negative. This is always positive. Like the learning rate is always positive. Like the learning rate is between 0 and 1, right? So, no, actually not. Sorry, the learning rate can also be higher, but it's at it's minimum at 0, right? It's minimum 0, because it cannot be smaller than 0. So we will talk about what the learning rate does in a second. Okay. So you can think of that this thing right here, the derivative, gives direction, and the learning rate gives the magnitude. So as I told you right here, we need magnitude and direction, and we have both components now. We have magnitude and direction. Like if alpha is very large, we will move faster. So alpha tells us how fast we're going to move down the slope, and the derivative tells us, hey, which direction, and that's it. Like in other terms, with in the training, like if we go to the training metaphor, our trainer, the derivative, is the thing that tells us, hey, how do we need to improve? Like, do we need to lose weight? Do we need to gain weight, for example, right? This is the direction, like depending on where we start. Like, are we too thin and need to grow muscles, or are we not too thin and need to lose some weight, right? So we're going to start either here or either there. And then this is how fast we're going to go, right? The alpha is how fast we're going to go. And as always, if you go to the gym New Year's, the alpha thing, the learning rate, is something you have to decide. Very important. So the learning rate alpha is our first real hyperparameter. So alpha is a hyperparameter. Hyperparameter, right? Hyperparameter. So, and this means you have to set it. So whenever we talk about hyperparameter, it's your job, and parameters are the job of the machine learning algorithm. Okay, all right. So, um, and this is the secret. This is the whole secret. But now let's have a deep dive on that, right? So, it's pretty clear. So here again, it's like it's set for you. So we have like this old parameter, right? Then we update it with a positive number, so we move towards the left. Now, if we have a negative number, right, so this is negative, then we move towards the middle. So it's important that we always move towards the minimum, right? And like this thing right here, the gradient descent algorithm, it's called gradient descent, because we move down the gradient, right? So the gradient obviously is that thing right here. So it's the derivative. It's actually the gradient is the vector of all derivatives. So we're going to move down this slope, which is the gradient, which is part of the gradient. So in my case, it's the derivative of theta 1, because we said we don't care about theta 0 right here. So it's the derivative of theta 1, which is the smallest gradient you could get. It's like one number. So we're going to move down here, or we're going to move down here. And either way, we're going to end up somewhere at the minimum. So, and I think this is like the most intuitive way on learning this. So we have a cost function. We have to determine like how can we kind of evaluate things. And once we have found something that we can use to evaluate things, we basically are able to say, hey, we're going to just move down that cost function, and it will be very cool, right? So, and this is basically how it works. Now, I want to talk about a little bit more about alpha. Like, it's pretty sure what this derivative does. It gives us the direction. Like, so we've learned this right here. So it gives us the direction. It says, okay, we have to either enlarge the value, or we have to like make the value smaller. Okay. But the alpha is the learning rate that determines how fast we go. And just using the sports metaphor, you know that if you train too fast, it's not good for you. But if you train too slow, it can take a while to be there at your goals. And it's the same in machine learning, right? So, if we choose alpha too small, gradient descent can be very slow, right? So we can take multiple steps. So our steps, so you remember this whole thing, like we need more steps. If alpha is slow, we have a lot of steps here, right? So, but if alpha is too large, gradient descent, we can overshoot the minimum, right? So for example, if this is too large, we can just go from here instead of going near the minimum, right? Instead of going near the minimum, we can just go on the other side of the cost function, right? Because we move like this instead of moving in small steps, right? So it may fail to converge or even diverge. Like the values will get larger in the end, but we want to converge like this. We want to converge it like this, so that we arrive at the value close to zero of the cost function. Say, okay, after a while, so we would determine, hey, the values of the cost function, they don't get any smaller right now, and then we would stop, right? They usually don't achieve zero in the cost function, but we're gonna say, hey, this is close enough, and we're gonna stop here if the values don't improve by an amount. So if the cost function only improves by a very marginal amount, then we're gonna say we're gonna stop. Okay. So this is the practical approach on how to stop this training procedure, and we can say, okay, we're gonna stop at this is how we're gonna come to this 100 here, right? For example, we're gonna stop, but this is like determined by, we're not gonna say we're gonna use 100 iterations. We can also do that, like this is totally possible, but usually we say, okay, the cost function, if the cost function improvement, like this is in time step t, right? So if the cost function improvement, if we say, okay, we have this cost function right here, this is in time step t, cost function of theta minus the cost function of t minus 1 is very, very small, like is smaller than some value, then we actually, so if this improvement right here, if we have an improvement from red to green, and the improvement is very small, we're going to say, okay, we're going to stop here, right? This has also some other advantages. Like for example, in neural networks, uh, we will stop way earlier. Usually, it's called early stopping, because we have then other things like overfitting and stuff that will go hand in hand. So we have some problems right here. We will talk about this in the evaluation chapter. Well, pretty cool. Okay, so and this is how it works. This is how gradient descent works, and this is the example of gradient descent for the linear regression, the easiest model, right? So basically, to summarize it, what we need when we want to train a model, we need a cost function. We need a cost function, right? We need a hypothesis, obviously, and the hypothesis contains parameters, and that's it, right? And then we're gonna use gradient descent algorithm to move down the cost function and basically get our final set of parameters after a while. That's it. So let's have a look. Let's have a look. So the important thing to know, right? When we look at this, right? So gradient descent can converge to a local minimum even with the learning rate alpha fixed, right? So if we have a fixed learning rate, this itself does not mean that every step here is the same, right? As we approach a local minimum, gradient it will automatically slow down, which makes sense, right? So it will automatically slow down because as you see here, the slopes are bigger here and they are automatically get smaller here, right? As you can see right here. So as you can see, the slopes are getting smaller and so the steps are getting smaller. Like it automatically takes care of that, right? So the only thing we have to do, so we don't need to decrease alpha over time. So we can alpha is a constant, very important. It's a constant thing we fix at the beginning, and the nature of gradient descent just makes it so we don't have to actually adjust it. But you can see here, this is a very large slope, right? A very big slope, and the slopes are getting flatter and flatter, which means the steps are getting smaller and smaller. This is automatically how it's done. And this is pretty cool. Yeah, and that's basically it, right? So this is the gradient descent algorithm, and this is how it's done, right? So what you basically do is you're gonna put the gradient descent, and if we were to like calculate it, right, for the linear regression, like this is for linear regression, we repeat until convergence. So this is for the two parameters. Like this was the general, as you know, this is the general formula, right? So this is the general formula. Actually, this is the theta one. Wait, where's the general formula? This is the general formula, right? Repeat until convergence. Like theta j minus alpha, then the derivative of j of with respect to theta j. And now, if we do this for the regression and we actually fill in the derivative, so we know we can calculate the derivative here, we will see that this is the actual kind of equation for that. But we don't need to know that. It's very important that the focus for us is to understanding how gradient descent works, because this is now very specific to linear regression. Now, this will look way different when we go to other forms like neural networks, or when we go to other regression models, right? So it's very important that this here is very specific to linear regression right now. So it's maybe not completely true because this kind of form is also true for logistic regression. But in logistic regression, we have a different cost function, and we will see that. We will have a different cost function, and therefore, these formulas will be quite different. So the only thing basically changes, so this gradient descent thing right here, this thing right here doesn't change. This doesn't change. It's always the same idea, right? So if you think, hey, but what about the neural network? It doesn't change. It's basically the same thing. It's harder in neural networks to get this derivative, obviously, right? And we will talk about how we can go there next semester. But the only thing that changes is basically the cost function and yeah, of course, the derivative of the cost function, right? But this is the general idea, and this holds true to no matter what kind of machine learning model you have. So this is the basic idea of how machine learning works with gradient descent. And I think like this is if you once if one time you've like have this in your head, then you know how machine learning works. And you also can see the problems that come with it. Like one of the problems we discovered already, like choosing the learning rate. This is one problem. Then some other problems like what happens if we change the cost function and the cost function doesn't look that nice? Like what happens if the cost function looks like this? So it has certain local minima and one global minima. So we want to end up here. But what if we get stuck here? So you can see there are many, so it's not always that easy, right? So this is why we started with linear regression, but the idea is always the same. We just have to try to fix so that we have a cost function that really helps us understand the problem and really gives us like a cost function more like this, right? Where we have more chance to actually uh, come up with a global minimum and something like this, right? Or at least have the chance to get somewhere here. Sometimes this is not guaranteed, right? But for linear regression, it of course is, right? So, and having said that now, you have a convex function. So necessary condition converge to global minimum. I just said that. So, and now what we have here is we actually have to create a descent example for our Portland data. So as I said, the data is completely real. And now you can look at, so on the left-hand side, we have our model. So we see our actual model in the two-dimensional realm where we have our y variable here. So this is so blue is our hypothesis value. These are our data points. So this is our training data. This is the current hypothesis. And here, of course, are our feature values. And you can see where we are here in that. So this is a two-dimensional version of this. So you can see exactly where we are. Remember, we want to go there, right? And so this is just an idea so that you know, okay, we are here. So this was the first point. This is the first point. Now this is the second point. And you can see how we slowly move towards the middle here. And in the end, we're going to end up exactly with that model. So this is the final model. These are the final values. And yeah, this is it, right? And now we've trained our model with gradient descent, and that's it. Okay. So it's really, really cool. And this is basically true, as I said, for all the mods. The only thing that changes is the cost function, right? So the only thing changes is the cost function. So now what happens if we move that from a regression task, because we started with, and like if I scroll all the way to the top, like we started here with the Portland housing prices, which was a regression task, right? Now, how does this change? And this is fairly important to discuss because I told you, well, it depends on the cost function. Now, what happens if we have another form of hypothesis, in other words? Like, how does this change and what keeps constant, right? So what happens if we have a classification in our hands, right? So now what we did is we did it for regression tasks, Portland, Oregon. Now, what if we do a classification? And with the classification task, we know it's about like having a model that gives us now discrete choices back, for example, email spam or not spam, online transaction fraud, non-fraud. This could also be they don't have to be like a classification doesn't have to be binary, right? So here we only have examples for binary classification, right? But it can also be many classes like here, right? It can also be 4 or 5 or 6. It doesn't matter. It's also a classification. Now, these examples here, specifically, these three examples are examples of binary classification, where it just means that we have only two objects, only two classes. So you can imagine we have two buckets and we have a model that needs to select, okay, either that's this bucket or that bucket, right? So this is binary classification. So binary classification. Okay. So And now this is it's pretty much the same thing. So as we go from, remember, the Portland housing data, now what we have is we have another example where we want to determine whether a tumor is, so it's this case that we are looking at, whether a tumor is malignant or benign. A very important thing in healthcare, very important thing in diagnostics. Is the tumor malignant, so it's very bad, or is it benign, so we can, so it's not that bad? So malignant or benign tumor. So, and now if we draw this whole thing, right, I can also draw it maybe in a clean way. So what's the difference to the regression, right? So if we look at the regression, so I'm gonna put a regression up right here. So in the regression of the housing data set, this is what our data points look like, right? So we had the size in square feet, right? And here we had our selling price. This was the selling price of a house, right? So, and this was like one data point. So one selling price to a size of in square feet. Now, in this case, the difference is that for X, it doesn't really change much. So we have a tumor size in millimeters, for example. And this is also a number, right? So this is like here it's size in square feet, and here it's the tumor size. So this is also a value, so it can take up all the values. But now, what's the difference with the Y? What's the difference here? Now, as we said, we only have, now the data says we only have two things, malignant or benign. So what's the difference between this one and that one? So you can see I haven't drawn anything. What's the difference in the y-axis? Now, the x-axis is not really different, right? It's both numerical scaled normal variables, right? But what's the difference in the y-axis? Now, this is actually benign or not benign, which we call it malignant. Yeah, malignant. So this is basically our y variable here, and this is our x variable here. As was this our x, and this was our y variable. Now, what's the difference here between this axis and this axis? Yeah, exactly. There are only two y variables. What you mean to say is probably there are only two values, right? So there's only one variable, but there are only two values, right? So exactly, Tristan. Tristan is completely right. So we can only have two values now. Now for the only thing, so basically I have two kind of lanes here, if I'm to say. So we have benign. So is the tumor benign malignant? So we can say, hey, is the tumor malignant? Yes, it is malignant, or no, it is not, right? So can only take up these two values. Like there are no other values Y can take. Okay, so my training data basically looks like this. I have Y and I have tumor size. So tumor size can have all different values, but Y actually also only says yes or no. Yes, no, no, yes, and so on, right? So this is how my data looks like. So can only take out two. Basically, we have these two lanes, and now we have tumor size. And so we can say, okay, so actually no, we say this is no. So we can have, like, we have these two lanes, basically, no and yes, right? So usually no is 0, right? So usually we code this as 1 and this as 0. So it's the actual 0 line. So let's say this is the 0 line, which is actually the axis here. So, and then we have like, can look like this, right? So the values can only be on this lane or on that lane. They can be like, we don't care about this, but here we can. So for example, we cannot have a value here. That's not possible, right? That's just not possible. We cannot have a value in between. So this is the idea of a classification, right? So we only have these two. And now let's say, hey, let's just assume, because we just learned it, we use the same thing. What we're gonna do is we're gonna just use what we just have used, we're gonna use a linear regression for that, right? So linear regression, right? Linear regression. So we're gonna use the same thing, theta 0 plus theta 1 times x, which is tumor size, right? So here we have the vector notation. So don't worry about it. This is the vector notation, right? So this is then the data matrix, right? So this is it's a linear combination, and it can this is true for all the variables. Like if you know vector, this just means theta times theta 0 times 1. So x basically is the data matrix with a column of ones here, and then this is actually just a column of ones. Then there is x1, x2, x3, and so on, right? So this is x. This is the matrix x, right? And then we multiply it. If we multiply it by the transpose of theta, right? If we multiply it by the transpose of theta, which is our parameters, we have theta 0 times 1, theta 1 times x1, and so on. So this is how it basically works. And then you can see, and this is our model, so we can like just express it like that, right? So this is just the vector writing if we have a model with a lot of x's. But for now, since we only have one x variable, I can also write it like that, just to get your mind a little bit on how vector notation works. But yeah, we could also write it like that, like we just did before. It's the same thing. Okay, we only have one variable. Okay, now what we could basically do is we could say, okay, we're gonna use a linear regression model, right? So linear regression model, we know that looks something like this here. So it could be something like this. So this is the linear regression model. We could use it as our hypothesis, right? So let's think about this. So we could use this. The problem now is that whatever model we use, we get a real value. Like this one spits out values, right? It's a regression model, so it spits out values. And so what we need is a so-called threshold, right? We need a so-called threshold where we say, okay, if this thing is, for example, larger than 0.5, then we predict 1 or yes. And if it's smaller than 0.5, then we predict 0, no. Okay, so this is a threshold we need to implement. So because our original data is only yes or no, right? But we will get a value from the regression, right? So this is like an idea that we have. So now the problem is, why can't we use a linear regression, or why would it be bad to use this hypothesis form? It's not like out of the world to use it, to be honest. It's not out of the world to use it. The problem you can see here, like for example, if we add a value right here, like this one, this x right here, as we know from the Anscombe quartet that we saw from the data problematic, it will basically shift this line right here to this line right here, right? And so although the actual idea is this one, is this one right here, where we say, okay, this is the size probably, this is it, where it kind of goes from no to yes, right? But our regression will have many problems. So first of all, it will have values that are below 0. As you can see here, there are values that are below 0. There are values that are larger than 1 also, right? So this is a problem. And so the problem is, if we use a linear regression, like if we use linear regression, that it can be that our hypothesis can be larger or smaller than 1 or smaller than 0, which is not what we really want, right? Because it can only be like, we want to sort of be within the realm, right? So what we're gonna do is we're gonna change to a thing called logistic regression, right? So we're gonna change to another form of hypothesis. So when I talk about logistic regression, I'm gonna talking about change form of hypothesis, right? Remember, in linear regression, this was our hypothesis, right? So we have our hypothesis was this one right here. This was our hypothesis. And now we're going to change the form of the hypothesis to fit it better, right? So, and now since this will take up a lot of time, we will start discussing this in the next lecture. But let's see, we have a question here. It's too sensitive to outliers. Yeah, exactly. Tristan is right. It's too sensitive to outliers. It has many disadvantages, right? But the basic idea is that the values the function can take on, right? So the problem is this right here, basically. So we basically the linear regression hypothesis, right? This one right here, the linear regression hypothesis, right? Linear regression, the linear regression, the linear regression hypothesis can basically take up values from minus to plus infinity, right? This is really not what you want, right? This is not, it's not really good. It's too sensitive to outliers because we don't really care about, we just care about the outcome here, right? So we don't assume that this thing is somewhere on top of you. It's still on the same lane. As I said, we only have these two lanes, right? Right here. So the linear regression is not a good idea. So what we need is we basically, and this is the motivation, and this is the last thing I want to put out there today is so the logistic regression, we will get to know it in the next lecture. But the idea is to avoid that. The idea is to avoid that and to basically have that. So we want to find a form of a hypothesis that squeezes, that I'm saying squeeze, that squeezes the value domain. So the domain of values that our hypothesis can take on between 0 and 1. This is what we want. So we are looking for a function, right? So we are looking for a function that can squeeze our x, right? Because our x, and this is very important, our x can also be minus infinite, plus infinite, potentially, right? I know you would say, but the tumor size is not like plus infinite. Yeah, potentially. The domain is the values it can take on potentially. That maps a variable that can be minus infinite, plus infinite to a space of that. So that maps it to that space, right? So basically x-axis can be anything, right? Can be anything. So this is our x-axis, can be anything, minus infinite, plus infinite, but we will squeeze it. We'll have a function that will squeeze this between 1 and 0. And this is the idea, right? This is the idea. Because it's a classification. We have malignant or benign. We have 0 and 1, right? And the idea is to not get, and this is very important. I cannot stress this enough because this is kind of complicated and mathematically very infeasible, is to get a function that actually only puts out values 1 and 0. So it's very important. We're not looking for a function that only puts out values 1 or 0. This will not happen, but between 1 and 0. So our hypothesis, whatever it looks like, our hypothesis of the logistic regression is can still have values like this, right? Can still put out values like this, 0.42. But then we can actually use the concept of the threshold in the manner it's supposed to be, because then we can say, okay, we will have a threshold a threshold of 0.5, which is in the middle of 0 and 1, right? So it's symmetrical. And we say, okay, if our logistic regression function is smaller than 0.5, then we will put it into the 0 class, which is the benign tumor, right? And if we have a value that is, for example, 0.81, right? Then this is larger than 0.5, which is our threshold. Again, we choose this threshold, but it's kind of common sense. Larger than 0.5, so we're going to put it into the 1, and we're going to put it into the malignant, right? And next time, we will learn how this function looks like, right? How does the function look like? How does the cost function look like? And the cool thing is, I do not need to say how do we perform gradient descent, because it's exactly the same way. So I never ever again need to actually tell you how we do gradient descent, because it's always the same. This is the beauty of it. Like I told you once, and it's always the same. So the only thing we need to learn for the models is how does the form of the hypothesis look like? This is obviously important. Like how does so these things, this is the way. So we need to know how does the hypothesis look like? The parameters, okay, they come from the hypothesis, we decide this. And then how does the cost function look like? The goal is always the same. So basically for every new function, the things we need to determine is always the cost function and the form of the form, I'm going to include form of the hypothesis, right? So, and they are usually a package, like people have thought about that, right? So people have thought about that. So the things I teach you for the specific models like linear regression or logistic regression, we not only learn how it's done in general, so this is how it's done in general, and the gradient descent, how it's done in general. So when we look at the general formula of the gradient descent, so this is the general idea. This is the general like gradient descent, but also how it's done with linear regression and what does it look like. And of course, we will learn about the cost function of what is called a logistic regression. So the form of the hypothesis is called a logistic regression, but this we will talk about next time. So, but before we stop here, a little heads up what we're going to do. When you look into because the exam is approaching, I know I get some mails about that, but not too many actually. So I'm not really afraid, and you should be neither. So we'll have a couple of lectures before the semester ends. So what we will do is I will, as I announced in the exam information that you should check frequently, I will put out a mock exam that we will talk about in the last lecture. So the last lecture will be about, we will talk a little bit about evaluation in the last lecture. We don't need, I think we need an hour for that. And then we will take the last half an hour or maybe an hour. So it will go a little bit longer. And we will do exam preparation right in the last lecture. And before that, I will put out a mock exam that will be in e-learning, and it will resemble the live exam. So it will be the same, like you can click on it e-learning, you can fill it out, so you get a feeling on how the exam will be. The live exam will be exactly the same, apart from the question, of course. So the question will be different. However, the manner in which it will be conducted will be exactly the same. The texts will be exactly the same, apart from that it says mock exam and not real exam, right? So some of the text. And we will talk about this in the last lecture, right? So we have so they have some ideas on how this will look like and how the exam will come to be. And also a notice that I also added in the exam information, it's an open book exam. You can use whatever you like, right? So you can use the slides, you can use the lecture notes, you can use ChatGPT, you can use whatever you like, okay? All right, so I want to make sure that as we slowly approach the exam, that this is clear, that what is our plan on preparing for it, what is my plan. And I said I will also compose like a cheat sheet that will be online, I think, next week. So it's just a summary of what's really important. So what's the most important things to remember and what are maybe less important things. I won't say and what are things that might not be relevant for the exam. I think it's only one thing because I didn't explain it, and I think it was the single value decomposition. or something in data preparation. But other than that, everything will be kind of relevant. But there are some things that are more relevant. So I will just like give you a cheat sheet on what's more relevant, and it will be up next or the week after, right? So you can use this also in the exam, and you should be best prepared then for the exam. Okay. Having said that, thank you very much for joining today. We'll see each other next week, and as always, now it's time for your questions. So please bear with me and ask away your questions if you like. Thank you so much.